Alright, so I'll be going over the level 3 and level 4 questions. And so the level 3 question is find the number of distinct ways 30 can be written in the form a to the power of b to the power of c, where a, b, and c are positive integers that are greater than 1. Okay. And so, first of all, it's 30 to the power of 30 to the power of 30. And so that means that a is of the form 30 to the power of n for some integer n. And so what that also means is that b to the power of c is equal to 30 to the power of 30 divided by n. That means that b to the power of c can be written in the form 2 to the I times 3 to the power of j times 5 to the power of k for integers I, j, k, such that I, j, and k are between 0 and 30. And so first we can look at specific values of I, j, and k. And so the possible values of c are just when the GCD, the GCD of I, j, and k is a multiple of c, or c divides the GCD of I, j, and k, with the additional restriction that c is not equal to 1. And that's because in the problem statements, it's greater than 1. Okay. And so now, if c is greater than 1, then c divides the GCD of I, j, and k if and only if c is a divisor of I, j, and k. Okay. And so now, what that means is that for any specific c, divided by c, multiples of c in the range of 1 through 30. And in addition, there's also the value of 0. And so basically, we can cube this because this works for each of the I, j, and k. And however, we need to subtract 1 because we cannot have that I equals j equals k equals 0. And so this is the only thing that we need to subtract out. And all the other cases can work for a specific c. And so what that means is that this number is equal to the sum from c equals 2 to c equals 30 of the floor of 30 over c plus 1 cubed minus 1. And so if we calculate this out, we can do this bit by bit to find that this is just 16 cubed plus 11 cubed plus 8 cubed plus 7 cubed. And if you're wondering where the -1 here is going, there's obviously 29 numbers in this sum, so we can just subtract 29 at the end. So plus 6 cubed plus 5 cubed plus 3 times 4 cubed plus 5 times 3 cubed plus 15 times 2 cubed minus 29. And if when you calculate this out, you can see that this is equal to the number 7,041. Okay, yeah. So that's the question for level 3. The level 4 question. Okay. So show that for any integer n, there exists a unique q of x with integers with coefficients in the set of 0 through 9, in the set of integers of 0 through 9, such that q of -2 and q of -5 are both equal to the number n. And so first of all, one thing we can easily notice is that q of x is be written in the form of x plus 2 times plus 5 times p of x plus n, where p of x is some polynomial that can be written in the form p of x equals a0 plus a1x plus all the way to an times x to the power of n. And so this is just a way to write p of x. And so if we substitute this expression back into here, well, we can get the coefficients of x to the k in q of x is just equal to 10 times ak plus 7 times ak minus 1 plus ak minus 2. And this can only hold true when all of these indices are positive, which is basically just k is between n and 2. Sorry, not n. N. K is between, sorry. K is between m and 2. Okay, yeah. Okay. In addition to this, the constant term is just equal to 10a0 plus n. And so it's a specific integer in the range of 0 through 9. And since a0 through am are all also integers, so what that means is that and the value of n can uniquely define the value of a0. And because the number must be in the range of 0 through 9, so there only is one value of a0 that works. Alright, and so that means that n creates a unique a0. And similar unique for similar reasons. And so now we already know that. Okay, so next we can basically define. Okay, so now we already know that 10ak plus 7ak minus 1 plus ak minus 2 is some number in the set of 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so, and this is true because this is just equal to the coefficient of q, and we already know that coefficients of q are in this set. And so, that means that we can see that the coefficient that ak is can be seen to be equal to the floor of 7ak minus 1 plus ak minus 2 over 10. Okay. Okay. And so the reason for this is just because these are numbers from 0 to 9, so they can't really affect mod 10. So dividing by 10 and taking the floor will just see the same result. And so that also means that since we already know that A0 and A1 are uniquely created, can uniquely be chosen for a specific n, that means that A2 and so on can also now be two values. And so what that means is that P is uniquely determined. And since P is uniquely determined, we can substitute a specific value of P back in. And so that tells us that Q is unique. And so we're done. So does anyone have any questions? Okay, if not, I guess the guest lecture can start now.